in this problem, 3.4, number 17, it asks you to use the matrix you had. Matrix A in exercise 1 was given as -2, 1, 2, and 5. Time out. Does everyone have that as their matrix or no? So we all have that matrix. And then it also tells you that that matrix is a product of two matrices, right? This is called a matrix factorization. This is called an LU factorization. And the point of the section is that if you have an LU factorization, that helps in terms of solving equations and things like that. So they say that L, which is lower triangular, is this one. And they say that U, which is upper triangular, is this one. Okay? Now, problem 1 is all about solving AX equals B. And then I gave you 15, which is something else to do with exercise 1. But 17 is about how to find A inverse. Okay? So, I guess in number 15, I'll tell you what you do. Since A is equal to L times U, A inverse is equal to L times U inverse, correct? What does that equal?
U inverse, L inverse.
There's the shoes and socks rule that you guys proved last time we were here. Remember that? So you guys are comfortable with that? So basically, the idea of number 15 is find U inverse, which is easy. Find L inverse, which is pretty easy. And then multiply. That's the idea of number 15. Number 17 is another way to find A inverse. Okay. You guys probably remember me doing this. We made a matrix where we put A here and we put the identity over here. You guys remember doing this? And what you do is you do a bunch of row operations until what happens? You get the identity on this side, and then what magically shows up? Well, we said it's not magic, and we showed why. A inverse, right? So we showed this already. So what they're saying to do is, they say, look, this matrix, what's it look like? It looks like this. -2, 1, 2, 5. And then 1, -1, 0, 1. And what you're really doing is you're putting it into reduced row echelon form, right? And so they're saying what you're really doing is you're solving two different equations. You're going to solve how do I say this? Oh wait, I screwed up, guys. Do you see where I screwed up?
I was going to ask about
That's a 0. Okay. So you're going to solve -2, 1, 2, 5, 1, 0, and you're going to solve -2, 1, 2, 5, 0, 1. What they really say you're solving here is the equation AX equals, and what's usually used is E1. And AX is equal to E2. Have you guys ever seen these E's yet? Okay. So I should explain what those are. Sometimes they're called the identity vectors or the standard basis elements. I'd like to find what they call them in your book. Let me pause for a second and find that. So basically the way it works is EJ, when I say vector EJ, this is a vector with zeros everywhere. So it's a column vector, first of all, okay? With zeros everywhere except a 1 in position J. Okay? And what I'm going to say is that if you take so first of all, the length of EJ, have we done the length of a vector with you guys? Oh no, we haven't. We did that in calc though. So this means the square root of 0 squared plus 0 squared plus dot 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 plus 1 squared plus 0 squared. And sure enough, what do you get? You get 1. So if you were in a calculus class, I would tell you this is a unit vector. But you're not. You're not in calculus class. You're in linear algebra. But since you're in linear algebra, what I can tell you guys that I can't tell calculus is this. I can tell you that the set E1, E2, dot, 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 up to En forms a basis for Rn. The set E1 to En forms a basis for Rn. All right, guys, there's our new word, basis. What does that mean? It means two things. The span has to equal Rn, and also the set has to be linearly what? Independent, yes. So I'm going to show you how this forms a basis, and I think it's probably best to use n equals 4. So if n equals 4, then my vectors E1 looks like this. E2 would be what?
0, 1, 0, 2.
Mm-hmm. You guys okay with this? Oh man, you gotta tell me when I'm off the screen. I'm not doing so great with that today. I should be looking here, not there. So I claim that this is a basis. Well, for it to be a basis, any vector in R4 is in the span of E1, E2, E3, and E4. Do you guys agree with that? Well, because if I have a vector WXYZ, it equals W times E1 plus X times E2 plus Y times E3 plus Z times E4, right? Guys with me? Mitchell?
Yeah.
Zach?
Yeah.
Okay. So that's the first thing. I know that any vector's in the span of these things. Second claim is that E1, E2, E3, E4, this set, even though there's four vectors, I claim that it is linearly independent. Now, how do I see that? Here's my proof. Let me put these into an augmented matrix. I'm going to make the four vectors the columns of this matrix, right? And what I'm really doing here is I'm solving the equation C1E1 plus C2E2 plus C3E3 plus C4E4. And what do I equal 0? And what do I notice? This only has what? Yeah, the trivial solution. You could see that because there won't be any free variables because it's already in reduced row echelon form. Okay? In Calc 3, we don't call them E1, E2, and E3. We call them vector I, vector J, and vector K in Calc 3. But once you get beyond 3 dimensions, you're sure happy you don't have to use letters anymore because you'd run out. So that's why we just use E whatever. Okay? All right, back to the problem. That was a little diversion, but I think worthwhile. So the problem 17, do you guys understand? Basically what we're doing, instead of doing reduced row echelon form, we're going to solve each of these equations. AX equals E1 and AX equals E2. Now I'll do one of them for you, and maybe I'll make you guys do the other one. All right. So how do I solve AX equals E1? So the trick is that what you really have is you have L times U times X is equal to E1. Right? Because I told you guys we actually have a way of expressing A as L times U. We wrote that down on the previous page. I'll bring it back shortly, but not yet. So then what you do is you use the associative property. And then we're going to let y equal u times x. So y is another vector. It's whatever u times x is. And so we're going to solve Ly is equal to E1. Solve this first. Okay, so let me do that. Let me solve Ly equals E1. Well, that looks like this. L was 1, 0, where'd it go? -1, 1 times, we don't know, I'll call them y1 and y2, equal to E1, that's 1, 0. Right? But here's what's really cool, is you can use what the book calls forward substitution. That's the opposite of what? Back substitution. See, when you have an L matrix, look at the first equation. The first equation says 1 times y1 plus 0 times y2 is equal to what?
1.
No.
Or
1. Yeah. So we just learned that y1 is equal to 1. Just like that. And now we can use that fact and use the second equation. If y1 is equal to 1, the second equation says negative 1 times 1 minus 1 times y2 is equal to 0. So solving, I get negative y2 is equal to 1, so y2 is equal to negative 1. All right, I got my y's. So, I guess I'll finish right in here. y1 equals 1 and y2 equals negative 1. So now, what do we know? Y is the same as, so basically, this means that y is equal to 1, negative 1, right? But that means that ux is equal to 1, negative 1, and U is an upper triangular matrix. So what's the upper triangular matrix? It was negative 2, 1, 0, and 6. Okay. So this time I'm going to use back substitution. So what's the first thing we learn? We learn that x2 has to equal what? I agree. x2 is equal to negative 1/6. Put a negative 1/6 in here. That's a little more work. And I'm running out of room, guys. Let's see. Negative 2x1 minus 1/6, because it's plus 1 times negative 1/6, has to equal 1. Negative 2x1 is 7/6, so I'm getting x1 is negative 7/12. All right. Yes?
So why did you set ux equal to y?
Well, I knew that ux was equal to y. And way back at the beginning, what I was trying to solve is x. So after all this work, what did we finally figure out x equals? Negative 7/12 and negative 1/6, right? That's what we figured out. Now, is that good? I guess the thing to do is to show you on MATLAB what happens if I just use this matrix and say compute the inverse. You'll see that we are getting somewhere. And then the other question the book asks is this faster or not as fast? And the answer is this is actually a little faster, believe it or not, especially when the matrices get bigger. Or at least it's comparable. All right, so what was A? A was,
Negative 2, 1.
yeah, negative 2, 1, 2, 5. I need my semicolon or it's not going to give it to me. Okay, so there's A. And if I say, what is A to the negative 1 power? I better say inverse of A. Be faster. So it gives me that. Do we recognize these? Well, I bet you recognize this number, right? 1/6. And I would not recognize negative 7/12. Oh, I made a mistake, guys. Right? Because the inverse of A, I got the 1/6 right. Maybe my x1 was wrong. Here, let's go back to the paper and see if we get, we should get negative 0.4167. So let's see, the first equation said negative 2x1 plus x2 has to equal 1. That seems right. Ah!
You put a -1 in the bottom right of that. For the y equation, I believe.
Y2 is negative 1, is that right or wrong?
Yeah, L.
Oh, yeah. There it is. This should be positive 1. Thank you. That fixes everything. And so what happens is y2 is positive 1, right? And if y2 is positive 1, then what happens? This is positive 1, so x2 is positive 1/6, which is what we got. And if this is plus, then this should be 5/6, and so we should get negative 5/12. Let me check that. Negative 5/12. There it is. Okay. Thank you, Tyler. Good catch. So you could do the other half. Is that okay? All right. We'll let that go. So that gives you a help on problem 17, and we also learned some things.